Okay, so we're pleased to welcome Dr. Ramona Voigt, who has a long career in physics, and we are welcoming her to our final lecture of the MTV Summer School. Dr. Voigt received her PhD in physics theory at State University of New York at Stony Brook in 1989. She then spent time as a postdoc at Lawrence Livermore National Lab, and then at Lawrence Berkeley National Lab, and returned to Livermore in 2007. She's also been an adjunct professor of physics at UC Davis since 1995. She published her book, Ultra-Relativistic Heavy Ion Collisions in 2007, and her interests include heavy ion quarks, quarkonium, as well as her newer work in fission, which she will talk to us about today. She, along with Jorgen Randrup of Lawrence Berkeley National Lab, are the developers of the event-by-event fission model FRIA, which is the fission reaction event yield algorithm. Dr. Voigt is a fellow of the American Physical Society and has served in the executive committee of the APS topical group on hadronic physics for 6 years. She is known to explain nuclear fission to Girl Scouts and Boy Scouts, so we're hoping that she will explain it to us as well. So let's welcome Dr. Voigt. Ramona, the floor is yours. And for questions,
Fabulous.
we'll put them in the chat, and then we'll have Stefano moderate questions. Thanks.
All right, thanks. I was in, but then I disappeared again. I mean, I could see the slides, but then something went wrong. So I'm trying again. I'm not quite sure what to do now. So, Stefano, you have my slides up.
Yep.
There are 59 slides. Is that right?
1 second.
Yes, that's right.
Oh, well, okay.
Okay. All right. So I'm gonna, because I'm having trouble actually getting onto the Zoom I was on, but then it disappeared. I'm going to try to just go ahead and talk through the phone from what I can see of my slides on my computer, which means that you'll have to change the slides for me. Is that okay?
Yeah, absolutely.
Okay, so this topic is titled Modeling Fission in the Lab in the Universe, and we go to the next slide. So you've been hearing about fission this week, and you heard about fission also from my collaborator, Jorgen Randrup, at the beginning of the summer school. So now you get to hear me at the very end, and I'm sorry about the problems. But nuclear fission, I think, is really cool. I didn't realize how interesting it was when I first got into it. But to me, it's the epitome of the conversion of mass to energy. So the heavy nucleus splits in two and releases a large amount of energy. Not exactly what the ancient alchemists had in mind, but it is a form of nuclear transmutation because it changes one element into two others that are hot and excited, that then emit neutrons and photons. And it was discovered, what it actually was discovered by Hahn and Strassman, explained by Meitner and Frisch, who called it fission and analogy to cell fission in biology. And it's really fantastic for studying nuclear physics. It has a mix of dynamics and structure, and it also encompasses 3 of the 4 forces of nature. Next slide. So it's been 80 years since fission was discovered. So you might think we understand everything, but from what Stefano's been telling you this week and what you heard from Jorgen before, there's still a lot that's left to understand. And first of all, the previous measurements could really be improved a lot. The models that we started off with were very big, but the last two and there are new measurements that are challenging old results, and discrepancies that are being better understood. And the large-scale computing that's available now means that fission can be studied as a quantum mechanical many-body problem, and thus a true theoretical model of fission may be possible. But there's a long way to go before that really happens yet. So there are phenomenological models like fission event generators that are required to fill the gaps. And despite the number of people on the line right now, we can tell that there are lots of young people that are interested in this kind of physics, and there are many different ways you can learn about things and applications of fission. For example, the abundances of elements in the universe can be explained in part by fission recycling that I'll hopefully get a chance to talk about near the end. And for another, there are anomalies in neutrino spectra from detectors like Bay and double twos that can be resolved in part by studying fission product yields. Next slide. You still there, Stefano? Hello?
Yes. Yeah. Next, one slide forward. Yep.
Yeah, I'm just checking because it's so quiet. So only the heaviest elements on the periodic table fission. So the actinides down in the lowest row at the bottom, and those following that series are known to fission. And the next slide. So those last elements on the periodic table up to oganesson are produced only in the lab by very small samples of new elements. And their final decay step, as you can see from slide 5, is the fission event. So they beta decay and alpha decay over short periods of time, and then you come down to a nucleus that's already known that fissions, and you detect the fission products, and then you can reconstruct from the whole decay chain that you made a new element. So the elements 114 to 118 were named by the Livermore-Dubna collaboration that discovered them, and I think it's pretty cool because now there's an element named livermorium. So in addition to berkelium and californium. So next slide. Now, if you go beyond oganesson, that's kind of an interesting element because you then start a whole new shell. And the question is how far you go towards what is known as the island of stability and creating super heavy elements. So in nuclear astrophysics, it may have been created in fission recycling in the cosmos, but it's harder to detect in the laboratory because we need very heavy neutron-rich targets and high-intensity neutron-rich beams. So oganesson was produced with a californium target, I believe, and a 48 calcium beam. And to go beyond to that, you need a stable enough heavy nucleus to make a beam, and you need an appropriate target. And as you go higher and higher in mass number, it's harder to make those appropriate targets. And if you really are a stable part out here in where they have the SHE island, then those elements may have long enough lifetimes that counting them can be hard. I mean, from the previous slide, you saw that there are only a few events each that produced oganesson and tennessine. Next slide. So how are these heavy elements made in the cosmos? We look to stars like supernova, neutron, that's stellar explosions, and neutron star mergers for stellar nucleosynthesis. And you see it on slide 8 that the actinide region here is circled on the table of isotopes. And you also see that as you go, the black the black points are stable nuclei. So as you go up and proton number, the neutron number isn't equal to the proton number anymore, but it starts to bend over. And so that means that the stable nuclei generally have more neutrons than protons. And if you have too many, that's because if you have too many charges close together, the nucleus can't bind. And the heavy elements yet to be produced are short-lived, and there are more isotopes that you can make. So you can make those through nucleosynthesis, like on the next slide. So the R process sets up the abundances of elements in the universe that thus end up here on Earth. So as you go higher and higher in the R process, you have to start decaying down, and you get to eventually to fission. But then you have a bunch of neutrons around and elements that start building themselves back up again, and then you have another fission, and the cycle continues. And that's how you make heavy elements in the universe. On the next slide, slide 10, you can see that there's the fission fragment yields actually cover quite a range of the, they're in green here, and they cover quite a range of the table of isotopes, mostly on the neutron-rich side. And so now I want to talk about actually modeling fission. So, and then we'll get to the universe a little later. So slide 11 shows that fission involves many time scales. You start off very quickly with the entrance channel, like for spontaneous fission or neutron-induced fission or even protofission. And then you have motion that so that the nucleus gets excited by say the neutron coming in to form the compound nucleus, and to get that excitation say equilibrated, it starts moving the neutrons and protons around, and then you start to get a neck in between them and that neck gets longer and longer until you don't exchange neutrons and protons between it anymore, and eventually snaps. And then this whole part is governed by the strong force, including neutron emission. So prompt neutrons get emitted first. That's a strong interaction, so it happens first time-wise, but the neutrons are slower than the photons that are emitted electromagnetically after that. So the photons usually reach the detectors first, because they're traveling at the speed of light and the neutrons aren't. And then after the prompt emission of neutrons and photons, you have decays by beta decay that are important for these neutrino measurements that I mentioned before. Those are governed by the weak force, and that's a much longer time scale. So on the next slide, slide 12, and talk about different fission models. I already mentioned that a microscopic theory of fission is a long way down the road, and there are a lot of application codes that don't use Monte Carlo. They use deterministic kinds of models, and they usually need the average neutron multiplicity, the prompt fission neutron spectrum, and the fission cross-section, and don't really care about the rest of the event. And so they don't really worry about energy and momentum conservation. So go to the next slide, slide 13. The deterministic Monte Carlo code, the Los Alamos model by Madeline and Ness, is what's kind of the gold standard for evaluation of data that are found, like in the NDEF database. If you've heard of that, it's a compilation of nuclear data that includes fission spectra, but that are modeled only using the Los Alamos model. It assumes the most probable average light fragment and the most probable average heavy fragment with an average separation energy based on these fragments. and it uses an average energy, and the spectral shape is assumed to be similar to what we've assumed the shape to be for Freya, but it's all deterministic, and then there's a boost so that you get approximately the right spectrum. But this spectrum is sampled over and over in average fission events, like shown on slide 14, where those deterministic models on the left, you see it's like a black box. There's a blob where neutrons and photons are coming out. But a Monte Carlo, like Freya, our model, which conserves energy and momentum, we can keep track of all of the energy and momentum of each particle as it is emitted. So these kind of models are really much better for determining a whole event and looking for fluctuations and correlations and actually comparing to data. So next slide. So what we want to do, what we have done, trying and continuing to do with Freya, is to try to make a more reliable physics-based model of fission for astrophysics and other applications. Okay, so we started with the applications first, and then found out we could apply it to astrophysics as well. So that was pretty cool. So you need a lot of data for input and for model comparison, and we also need to have basic physics, including at the very minimum all conservation laws, and to realize that emissions are correlated and everything depends on everything else. So Freya models complete events based on data and theory input. On slide 16, they explain that this is event-by-event modeling is a very good way to model fission. And as Sarah mentioned, I have a book on relativistic heavy ion collisions, ultra-relativistic, in fact, much higher energy than we're talking about here by orders of magnitude. But in event-by-event modeling of those collisions, that you have high energy nuclear collisions with lots of different outcomes where you can follow the trajectory of all the particles and predict the outcomes of the experiment. So there are codes. There's a code called Pythia, after the Greek, that's been useful for studying detector response and predicting outcomes. And we sort of wanted our Freya to be a little bit like Pythia in this regard. And this calculational framework is easily adaptable for studying fission because, again, when you have many different fragment pairs produced in binary fission, then you have a lot of different possible outcomes that you can follow. And so Monte Carlo is tractable. So our goal was to have a fast generation of large samples of complete fission events, and I think we've satisfied that goal pretty well. We have a complete fission event with full kinematic information on all the final particles. The two product nuclei, we call them products because that's after the neutron and photon emission. That's when they're detected. And then the neutrons and photons that emerge. And the advantage of having these samples of complete events is that it's straightforward to extract any observable to take into account detector cuts and acceptances, and therefore make easy comparison to the data. And the advantage of it being fast is that it can be incorporated into other transport codes and used that way. So now I'm going to talk a little bit about the physics that's in Freya. So on the next slide, slide 17, before fission, where the nucleus actually splits into two separate fragments, neutrons can be emitted. And in the case of neutron-induced fission, with the energy infinite neutrons, the compound nucleus can be excited enough to emit a fission. And a couple of things that can happen. The first is that the incoming neutron kind of just barely interacts with the nucleus, just enough to excite it, and then gets kicked out again. And this is a pretty easy way of, distinguishing it, at least modeling wise, because there's a specific endpoint energy for this process. On the other hand, multi-chance fission is kind of interesting because while you have a equilibrated compound nucleus, but if the excitation energy is high enough, it can spit out one or more neutrons and still have enough energy left to fission. So that's what's shown in the bottom little figure there. You go from first chance at the bottom to second, third, fourth, and fifth chance fission. And what we do in Phi, if there's not enough excitation energy left after these neutrons get emitted, then we just start over with a different event. But this is one way you can emit neutrons ahead of fission. In addition to, I know Stefano talked about fission neutrons. It's a little bit, they've yet to be proven, but people like them. Next slide. So after this fission, we sample the fragment characteristics. So we use fragment yields based on data and modeling if we don't have the data. We need both the fragment yields that are shown on the left for different energies. So you can see there's a significant energy dependence. This is asymmetric fission. There are some nuclei that fission symmetrically, which means that they have a peak in the middle instead of this dip here that you see. And as you go up higher in energy, this dip kind of starts to fill in, and you get wider bands of wider range of fragments that are possible. So you get an elevation of the tails of the distribution for low and high masses as you go to higher energy. So this is thermal, a couple of MeV, and then 14 or so MeV down at the bottom, so high energy. But we also need a total kinetic energy, because that tells us how much energy is then available for neutron and photon emission, because the fragment identities give us the Q value of the fission, the total kinetic energy, and tells us how much energy is taken away from the fragment motion, and then what's left over is the excitation energy. So we are there's a lot less data on different on the total kinetic energy for different energies in neutron-induced fission. So next slide. So the total excitation energy that's left after the fragments separate is partitioned between the fragments as total excitation energy. And we start off with an empirical split between the statistical or intrinsic excitation and the rotational or spin energies. And this part is hard to get right because there's a lot of modeling involved and very little data. And there's not much energy dependence, like I already mentioned. So it's hard to do this right as a function of energy. Time to show this. The correlations between emitted neutrons, photons, and fragments can provide some additional information that can tell you something about the excitation energy. So slide 20, this is mentioned already, that total excitation energy includes both statistical and rotational energy. So the rotational energy is represented by this spin and the moment of inertia, and the statistical excitation by this E0 squared, E0 star, sorry. The pre-fission neutron evaporation gets treated the same way as post-neutron evaporation from the rotating fragments. We have a plane of rotation, and the impact is determined by where the neutron actually impacts the nucleus. And it may change due to pre-fission neutron emission and tilt relative to the pre-fission rotation plane. So I mean, there's a lot of angles and stuff to take care of. But once once the nucleus splits, the fragments follow Coulomb trajectories. And then on the next slide, we de-excite the fission fragments by neutron and photon emission. The neutron emission reduces the intrinsic excitation energy, but not the spin so much on a strong interaction timescale. The photon emission is assumed to begin after more neutrons can be emitted. You can introduce some competition between neutron and photon emission, but this is mostly going to give you some high energy photons that you wouldn't normally get otherwise. Photon emission is really what reduces the angular momentum on the electromagnetic interaction timescale. And then, as I already mentioned way earlier, on the timescale of weak interactions, the remaining fission product yields decay by beta decay and can then emit electrons and neutrinos. And so they you go on to end up with what are called cumulative fission yields, which are after a long time, and some of these beta decay processes have already happened. So fission is pretty unique. As I mentioned, through the four forces. So gravity is the only force that doesn't play any role in fission physics, which I think is pretty cool. So next slide shows the neutron evaporation from rotating fragments. We use a Weisskopf viewing an energy spectrum, and every time a neutron is emitted, we recalculate the temperature scale, and then so that means that we take care of the appropriate energy conservation, so that it could be that it could be that the neutron spectrum changes as there's a neutron multiplicity, so we always boost into the laboratory frame, and so we're conserving energy and moment and linear and angular momentum this process. So that's neutron evaporation. Next slide shows photon emission following the neutron emission, and we're assuming that once the excitation energy is below the neutron separation energy, then the only way you can get rid of the remaining excitation energy is by photon emission. And first, you can have statistical photon cascades. These are modulated by the giant dipole resonance, the formula shown on top. And then you either reach the Eros line, where you have these quadrupole transitions along this line, or if there is tabulated data that's in this Ripple database, we use the decay tables and take care of transitions between levels instead. And each photon gets Lorentz boosted to the laboratory frame as well. So that's, in a nutshell, the basic physics that's in fission, in Freya's fission model. The next slide tells you a little bit about what in Freya can be adjusted to data. We use, I said, isotope-specific inputs such as the yields and total kinetic energies. There are intrinsic parameters such as the nuclear masses. We use experimentally measured masses and supplement by masses calculated by Muller, Ness, and collaborators. And then we also need to have bearing heights, carrier energies, and shell corrections that are tabulated from models. And then there are external parameters that can be adjusted. And one is the shift in the total kinetic energy that we use to give the evaluated average neutron multiplicity. There's a level density parameter, the C0. Enters into calculation of the temperature. Energy balance between the light and heavy fragment. It's represented by a single parameter we call X. And this we learned something about from the neutron multiplicity as a function of fragment mass, or from neutron-neutron correlations. And then the next thing is the width of the thermal fluctuation that we use to adjust the excitation and total kinetic energies to conserve energy. The C has an effect on the neutron multiplicity distribution. And then we have a multiplier of the fission temperature, CS, that determines the level of nuclear spin and also the amount of photon emission. And then there are a couple of detector-specific inputs, which we adjust to match the experiment. The experimental detector qualification, such as the minimum photon energy that's detected and the time that photons are measured. It's called Tmax. And then so photons that have transitions with half-lives longer than Tmax don't get detected. So I've talked only about Freya, but in the next slide you can see that there are other Monte Carlo fission codes, CGMF, which is based on Los Alamos, Fiferland, which is a French code, and CGMF and Fiferland are based on Hauser-Feshbach theory that includes angular momentum and parity, as well as some overall possible outcomes. This seems to be a slow procedure, so CGMF and Fiferland take longer to run. The CGMF, Fiferland, and Freya all use similar inputs of the yields and total kinetic energies to extract the excitation energy. Now, GAFIS is somewhat different because it models the fragment yields and the fragment excitation energies. Instead of using TKE as an input, it's more of an output. So the next slide shows some model comparisons for the neutron multiplicity as a function of the fragment mass. And CGMF uses a different approach. They try to model the nu of A point by point, but they end up getting something similar to what we have for Freya that's shown on the right-hand side here. These are both for plutonium, and then the bottom row shows different calculations for californium. And I should mention that the Freya calculations that are shown here are not, those spreads are related to the Z's that are in access for a given A and don't have anything to do with the statistical uncertainties. So the next slide shows the neutron multiplicity distribution from Freya on the left and CGMF on the right. And the interesting thing when you look at the Freya calculations on the left is that the Poisson distribution is lower and shifted to smaller neutron multiplicities, and that's because it doesn't take into account the separation energy, just the average energy of the neutron. Another model thing to look at, and next slide, is the neutron kinetic energy as a function of fragment mass, and there are examples that are shown on this slide for Freya on the left and CGMF on the right. And that's something that's very dependent on how you do the excitation energy sharing as well. So now I want to switch to correlated observables. So slide 29 shows says that we're going to be looking at the correlations, and this is something that's really not possible to model without the complete event calculation. So the next slide shows two neutron angular correlations. So if you look at the angle between two neutrons, now if you assume there are at least two neutrons produced in a given event, they can either come from the light fragment, both from the heavy fragment, or one from each fragment. And that's what you see on the right-hand side. So the green curve is both of them coming from the light fragment, which had a higher velocity, and so you have a stronger correlation at 0 degrees. If they both come from the heavy fragment, you have a weaker correlation at 0, but it's still, and if it's both neutron, if two neutrons are one neutron, then it would be 80 degrees. And if you weight all of the possibilities, the black curve is shown. And on the left hand side, you can see that the correlations depend on the specified threshold energy. You can see the data for at the bottom, and on the right, there's some measurements by Jerome Verbeck for plutonium-240 spontaneous fission that show that Frey also gives quite good agreement, but we had to adjust this X parameter, and the tilt of the distribution for the correlations depends strongly on the X parameter. So even though we didn't have a measurement of nu of A for this nucleus, we could still get some information about that excitation energy sharing from the neutron-neutron correlations. On the next slide, we have correlations between neutrons and light fragments. So if the neutron comes from the light fragment, you get a strong correlation towards 0 degrees, and you get a strong correlation at 100. You see that there's more of a tilt towards 0 degrees overall. The left-hand side shows a combination of the various possibilities. The right-hand by Gook and collaborators compared to Frey and to JMF, and the agreement is generally quite good. So that's neutron and neutron fragment correlations. Next slide shows something about neutron photon correlations. And Stefano is the expert on this measurement-wise now, but he's been looking at event-by-event correlations between neutrons and photons, which are pretty cool because you don't need a fragment detector, but the neutron multiplicity and photon multiplicity are bent according to the event, and the data get integrated over the fragment mass and total kinetic energy. Whereas there are other measurements that have been done fragment by fragment, in some sense, in that they have the neutron multiplicity and photon energy bend according to the total kinetic energy and or fragment mass. So you need the fragment detector, but you don't do it event by event. The data get integrated to overall events. And the fragment-based results don't agree very well with each other at all. So there are new data that are required to try and kind of come to some reconciliation. The event-by-event results, thanks to Stefano, are reconciled, but it would be nice to have more data from both methods to try and reconcile all the results and see if they do agree in terms of whether they give a weak correlation or a strong correlation, a positive or negative, and so on. So now, finally coming back to the cosmos on the next slide, these R process calculations, all the R process simulations that that include fission recycling that I mentioned at the very beginning depend on a lot more than fission. So you model not just the fission, but also the accumulation of these neutron-rich nuclei. So you need to know something about the astrophysical conditions, neutron capture rates, nuclear masses, fission barriers, and all this stuff that's not really in any code consistently. So we have a lot of information, about about fission with Freya, but you also need all these other rates, like for beta decay and neutron capture and so on. And all this gets fed into nuclear astrophysics simulations, and then you get the abundance patterns of elements in the universe as outputs. So slide 35, I was part of a paper with Nicole Vash and collaborators based at Notre Dame, where we were looking at applying codes like Freya to the R process. But for the R process, I mean, you saw on the chart of the table of isotopes where you have many, many nuclei that can be accessed, many more than we have information for in Freya, for example. So the R process requires knowledge of fission yields for hundreds of these neutron-rich isotopes where we don't have the input data. But we do have the GEF code where they have a way of using information based on systematics to get the yields. And it's a function of DNA, and they also are modeling the excitation energy, so we can backtrack out and get the total kinetic energy and take the yields from GEF and run them through the R process simulations, but also take the yields from GEF and put them into Freya and do the same, because then we have a handle on how important the neutron emission is in these codes and in the astrophysical processes. So that gives us some idea of the sensitivity of the abundance patterns to neutron emission. And that's shown on slide 36, where the fission fragment yield can make a big difference in the abundance pattern. So what was done for a long time was only a 50-50 split, symmetric fission all the time, which as you can see from earlier on in the talk, where I showed these yields for plutonium as a function of energy. We know that's wrong because a lot of fission is asymmetric, and even so, it's never just a 50-50 split. But you can see that doesn't do a very good job of fitting the abundances. Those are in blue. There's another model by Kodama and Takahashi that involved overlapping Gaussians for the two distributions, one for each fragment. And then the GEF yields are shown in the red for the R process. Now, none of these include neutron emission so far. So on top, it shows the abundance as a function of mass, and on the bottom, it shows as a function of proton number. Now, neutron emission won't affect the proton number, but it can affect the mass number. So before I show those results, I'm just going to say something about differences in the neutron emission in GEF and Freya on the next slide. So I've already mentioned some of this, but GEF models the yields, and Freya uses the GEF inputs for our calculations. GEF models the fragmentation energy using systematics, which, it is what it is, but we don't model the excitation energy directly because we have the total excitation energy from the Q value, and using the yields and total kinetic energies and mass and energy conservation. Well, GEF gets the fragment total kinetic energy from energy conservation, and we get the excitation energy of the fragments divided between themselves using the X parameter that I mentioned that gives somewhat more energy to the light fragment. And GEF doesn't provide a lot of information about how neutrons and photons are emitted. It says it's done statistically, and it's kind of confusing if you try to look into it in more detail. Freya uses neutron emission according to Weizskopf-Ewing, And then photon emission first in the continuum statistically, and then according to the Ripple 3 database. So based on the way the de-excitation of the fragments is done, we can expect that we may have different neutron emission in the two models, and that is indeed the case, as shown in slide 38. We have on the left-hand side spontaneous fission, and on the right-hand side neutron-induced fission, and this is just a corner of the table of isotopes, where you see the Z above 80 on the left-hand, on the y-axis, and neutron numbers above 140 on the x-axis. So you can see that they're very different than just looking at the nuclear chart, the whole nuclear chart. And so Gas is on top and Freya is on the bottom, and you can see that Freya tends to emit more neutrons than gas, especially up in the very edges of the chart, where you might expect to see different, some change, say, between asymmetric and symmetric fission, and also where you get very far away from this idea that the split is that X should be greater than 1, and this is based around this dip in the nu of A that comes at around A of 132, where you have two closed nuclear shells, so you expect very stable fragments right there, and so little neutron emission. There may be another, so that's the reason why we have X greater than 1, but if you go far away from that, then that may not tend to be the case anymore. So how does that change the abundance pattern? That's shown on slide 39. So it doesn't change it a whole lot. If you look on the log scale, it's very difficult to see, but you can see maybe like 10 to 20% changes in the abundance pattern. And if you look at the next slide, slide 40, you see that there's we have some discussion about the incident energy and neutron emission dependence. So the sensitivity depends on the yield and on the neutron emission, and you can see how it affects the percent differences down below. And on slide 41, you can see that there's also dependence on the nuclear masses and fission barriers. So the curves for fissions go way up for the liquid drop model masses and barriers relative to gas. That's shown on between the left and right hand sides of that figure. So now I come to the last slide, and this is just references for the prior papers with more in progress. So are you all still there? Any questions?
We're still here, and yeah, we do have a few questions in the chat. Maybe we can give a few minutes to people to post a few more questions, but we can start also with the ones that are already here. And thank you so much for the presentation, Ramona. I know it was very hard to get all the communication going, but this was very interesting, I think.
Yeah, I'm very sorry about that. It's very strange because I was actually on a Zoom presentation for Girl Scouts yesterday, and I had no problem.
Yeah. So we can start with an easy question. The first question is, are there any fission reactions with equal masses of both fission products?
Yeah, okay, so the 50-50 split is rare, I would say, because even if you're basically having symmetric fission, you still have you have a peak at symmetry, but then you have some variation that falls away. You can describe by some Gaussian distribution, perhaps. So, I mean, if you look at the paper that we did with Nicole, that I was just showing results from, Jeff does have some transition between asymmetric fission and symmetric fission, and you tend to have somewhat more symmetric fission as you go, say, higher in Z and N. So up in the corners of slide 38, where you have high Z and high N, then you tend to see more symmetric, according to Gaff. If you use a different method of obtaining the yields, you don't necessarily see that. And you tend to see more asymmetric fission all the way across. Is that okay?
I think that the person didn't reply, but I think this is a very good, a very complete answer. And I'll encourage everybody else in the room listening in. If you have any questions, please post them in the chat. We have one other question that is already here, which is from Dr. Clark. For the fragment excitation modeling, you mentioned that photon release happens only when neutron release is no longer possible. Can you comment further on the physics behind this treatment?
Well, okay, so I mean, you can. So if you go back to slide. Well, it's say if you think about so if we go back to slide 17 where you see the multi-chance fission, we determine whether there's a multi-chance and whether a neutron is emitted before fission based on the branching ratio for neutron emission and fission. So that's a gamma n over gamma f. And you can do something similar for photon emission versus neutron emission, the competition, by calculating the branching ratio or probability for photon emission versus the probability for neutron emission. And you're going to have some area of where they're competing anyway because they're very close to the neutron separation energy. But that will give you a definite sort of residual energy that's left over, that's where photon emission is going to dominate. And even if you include this competition, it's going to still probably give you more neutrons than emission at the beginning than photon emission. So the biggest difference I would say in Friday, because of this, is that we may get very high energy photons because we're only limited by the residual energy after neutron emission. So nothing much more than the neutron separation energy. But if you allow the competition and you have you can have higher energy photons that can be emitted before a neutron perhaps, and then they will carry more significant amount of energy and would show up as in a tail of the fission photon spectrum. Hello?
Yeah, sorry, I had to mute it. So we already have another question, which is from Professor Pozzi. We frequently measure californium-252, the spontaneous fission. What can these measurements of californium tell us about plutonium-240, also spontaneous fission? So how well
What can California tell us about?
Yeah, so how does California, what does the spontaneous fission of California 252 tell us about the spontaneous fission of plutonium 240?
So, I mean, if I'm thinking about it in terms of model parameters and Raya, I mean, we've learned sort of that that there are things that depend strongly on the isotope, and some things that so if we look at the parameter values that we get, I don't have that a slide on that here, I'm pretty sure. No, I don't. But so if you look at this, at slide 24, about the parameters that can be adjusted to there. I mean, if we fit, say, the parameters, these 5 parameters to Californium, we don't expect the E0 and CS to change very much. We expect that because the average neutron multiplicity between Californium and 240 is different. You know, plutonium 240 has a neutron multiplicity that's a little above 2. And so we expect that the neutron multiplicity distribution, you know, P of nu, is probably not going to be fit with the same value of the C parameter. And we may have to adjust the DTKE between them. But we had assumed that we could use the same X parameter between Californium and plutonium 240, and we found out that we couldn't. Say from slide 31, I had mentioned that this tilt of neutron correlation that's shown on the right, we had to change X between Californium and plutonium to get a good match with plutonium measurements. So, I mean, the physics is the same, but some of the details in terms of the parameter values can differ. So we know from modeling Californium that we can get the physics pretty much, but the details for the parameters actually matter from nucleus to nucleus. So we didn't find, like I said, much of a variation due to photon emission, but we did find some in neutron emission. So I hope that helps to some extent. So it'd be good to measure both.
Yeah, I think that answered the question the chat indicates. So, and it also looks like there are no more questions in the chat. So unless there are some last minute questions that people want to ask, we can thank the speaker again. And yeah, and also thank you all very much for coming to these presentations. This was the last one of the summer school. So I hope you've had a good summer. And thank you, Ramona.
Yeah, I apologize that I couldn't actually show myself because of my weird computer problems. I'm very sorry about that. I would have liked to see people instead of sitting here talking into my phone. But I appreciate being asked, and I really enjoy collaborating with Professor Pazzi and the group. And so I'm looking forward to seeing some of you actually in person sometime.
Absolutely. Okay, well, with that, I will now end the recording, which actually I think, Sean, you have to